All right. Yeah, so my name is Rúnar. I'm going to be talking about compositionality. So the plan for this talk is to tell you what compositionality is. I'm going to give you a contrived example or two. I'm going to dazzle you with some category theory. I'm going to tell you what homomorphisms are, which I think is the take-home point of this talk. So if you take nothing else away, then just think homomorphisms, and if you understand that at the end, then we've succeeded. I want to talk about some things that prevent composition. Obviously, I'm going to talk about monads, and then the plan is that you'll be inspired to write more compositional code. Okay, so what is compositionality? So the sort of Wikipedia definition is that software is compositional to the extent that we can understand the whole by understanding the parts and the rules of composition. So we're going to construct compositional software from some modular pieces that we can individually understand. That's what's implied by this. And if we understand the pieces and we understand how they're put together, then we understand the whole program or the whole system. So a compositional program or expression is going to be a nested structure. So it's going to be an expression at sort of every level of nesting. And then each expression, each sub-expression, is going to mean something. And the meaning of the whole expression, the overall program, is going to be composed of the meanings of the sub-expressions. A concise way of saying that is that the composition of the meanings is the meaning of the composition. So note that there are two notions of composition here, and it's sort of a punning on composition. So there's composition in the expression space, so composition of programs, and then there's composition in the meaning space, or composition of meanings. And compositionality means that these compositions of programs and meanings, of structure and interpretation, or syntax and semantics, that they should mirror each other in some sense. Note that I'm saying compositionality and not composability. Right? So I think composability doesn't capture as strong an idea as compositionality. It sort of conveys that something is able to be composed. Like, if you write a bunch of other code and glue things together somehow ad hoc, then you can compose these things. But that's not what I'm saying. Compositional expressions are natively and fractally composable. In fact, I want to say that compositional programs do nothing other than be composed. That is all they do. Okay, so here's a cool program I wrote. Purely functional, obviously, right? No, so this program, I mean, it's fine, but it's not very compositional. The parts, you'll notice, of this program are not complete programs in and of themselves. And each sort of part of this is not meaningful without all the other parts. So in order to understand what any of the parts here are doing in the overall program, you need to read the whole thing, or at least most of it. So what this does is that it reads a file from the file system line by line, and then it counts the number of words in that file, and then closes it, and then prints out the count. Right? It's not totally obvious, but that's what it does. So here's another program that does the same thing that I wrote using the FS2 library, or functional streams library for Scala. And so it does the same thing. It opens a file called the file.txt. It counts the number of words in the strings in the file and prints it to standard out. But notice here that this is now compositional. So every part of this is meaningful in and of itself. So this top part here, io.lines are the file.txt, will open a file, and it will produce a stream of the lines in that file. And it will do this regardless of what else is around it. And this next bit will take whatever string comes in, and it will split it on word boundaries, or on white space, and it will emit the words that it saw. And this will work for any stream of strings, right? So this is meaningful in and of itself. This will replace any the elements of any string, of any stream with ones. This will sum up any stream of numbers, and this will print any stream to the standard output. Right, so all of these are meaningful expressions in and of themselves, and the meaning of the whole program is a composition of the meanings of these sub-expressions. So the whole thing has sort of the same character as the parts. Every part of this is a stream. And the logic is very prominent, I want to say. Like, it's just looking at this, it's kind of obvious what it should be doing. And it's also easy to verify. The correctness of this program is sort of composed of the correctness of the parts. That is, as long as each of the parts is correct, that I've correctly arranged the parts, then I can conclude, sort of compositionally, that my program is correct. That it does what I mean. Cool. So yeah, every part is a meaningful expression, and I can just sort of emphasize that by putting each of the parts into its own value. And these are just perfectly good Scala values. And they become functions. And then my whole program is a composition of a bunch of functions applied to a single input. And in compositional software, we ideally want this property that we are applying a single composite function to some input. So compositional programs are sort of naturally modular. All right, so I've written that here explicitly, that, you know, the function f, which is my program is just f applied to the lines, and the function f is just print composed with sum, composed with ones, composed with words. Cool? So this works because functions are compositional. And I want to say that functional programming is really the study of compositional software. Like, it's really taking the idea of composition seriously, of compositionality, and taking that to sort of its logical conclusion, taking it all the way to the end. The way that function composition works is that, so if we have a function f that goes from a to b, and we have a function g that goes from b to c, then we have a composite function g compose f that goes from a to c. Right? It just does it does f and then g. And it's, you know, implemented by lambda of x, g of f of x. Right? But we say that this diagram commutes, by which we mean that all paths through it are the same. And composition of functions is associative, which is a useful property, in that it doesn't matter if we consider f compose g first or g compose h first in the expression h compose g compose f. All the paths through this diagram are the same. They are a function from a to d, which does f and then g and then h. Okay? And then also for every type, there's going to be an identity function that does nothing. And then what it means to do nothing is going to be made precise by this notion that composing the identity with any other function is going to be that same function. So f composed with the identity is f, and identity composed with f is also f. That is, these diagrams commute. So whenever we have this kind of structure, this sort of compositional structure that is associative and has an identity, we have what's called a category. So a category just consists of some objects. We have some arrows between the objects. We have composition on the arrows, which is associative and has an identity. And that's all of category theory. So if you didn't know category theory before today, or before yesterday, now you do. So Scala forms one of these, a category, where the objects are the Scala types. The arrows are Scala functions, so just functions that take values of those types and return values of some other types. And composition is just function composition, which is associative and has an identity. Right? So it's definitely a category. And the plot of category theory is really about composition. So category theory is really the abstract study of what kind of things we can compose. What kind of stuff is compositional? which is to say what kind of stuff is like functions. So let's take a simple example of a compositional thing, which is a monoid. A monoid is a special case of a category. So a monoid is defined in subtype M, and it's going to have two methods. One of them is a binary operation called append, and the other one is a value, which is going to be an identity for that operation. So we're going to understand that as the empty value or the 0. All right? So yeah, a monoid is a type. It's an associative binary operation, and it has an identity element for that operation. So examples are int with plus and 0, int with multiplication and 1, booleans with and and true or false, string with plus and the empty string, and then functions on the same type. So the function from A to A for any type A with compose and the identity on A. All right, so all of these are monoids. Another way of saying this is that a monoid is a category with one object. So another way of saying that is that a category is a sort of generalized monoid. It's like a monoid where not all the elements are compatible with one another. So yeah, monoid is a category with one object where the objects are just the type M. The arrows are the values of type M. Composition is the append for the monoid, and the identity is the empty element. Right? So the arrows in this category are not functions, they are values. And so we're going to have the same kind of diagram situation as we did with the functions, where if we have an element x and an element y, so imagine that these are strings, right? So we have a string x and a string y, and we want to concatenate them together, and I say y compose x, which really means x plus y. So we have a composite string, which is, x, y. And notice the arrows are meaningful. That is, the directionality of the arrow tells me which string comes first in the composition. And then there's an identity arrow, which is the empty string in the string monoid, or is 1 in the multiplication monoid. And I'm denoting the one object in the category as just star. Okay? So monoids form a category. And composition in a monoid is associative. That is, it doesn't matter which way we consider the parentheses in the expression, z times y times x. We can arrange the parentheses any way we want. So monoids are great for processing data, for large amounts of data. And this is an example where compositional reasoning, which I'll get into what it means, really helps us. So imagine that this is a really large document. Let's say it's billions of pages long. And we want to count the number of words in here. Cool. So one strategy might be to split the input, so divide and conquer, right? So then we can count the words in each subproblem, possibly in parallel, and then we can assemble our results at the end. So we can compose our results at the end. So what we want to do is design a monoid so that we can count the words and then return that in some data type, which is a monoid, that we can then assemble at the end. And so since we want to be able to compose the subsolutions, we want this property, which is a sort of compositional reasoning, that appending the word count of S1 to the word count of S2 should be the same as word counting the concatenated string S1 plus S2. Make sense? Like there should be as many words in the concatenated string as there are in the two strings together, right? So the word count of the whole is a composition of the word counts of the parts. So we need to design our monoid in such a way to allow for composing these partial solutions. So a thing that might happen when we're doing this is that we might split in the middle of a word. And so we got to be careful to design our monoid in such a way that we track the sort of junk, that the non-complete words that we might see, because we don't know whether we're looking at the whole string. So for example, here at the beginning, I don't know whether the first word is a complete word. All right, so that lorem thing. So in my word count, I actually want to track that I saw an incomplete word at the beginning. I saw 39 complete words, and then at the end I saw a space or something. So I didn't have a partial word at the end. And I'm going to do this for all of the parts, and then I end up with these sort of partial solutions, and then I want to assemble my partial solutions. So to add together the first two results, I just sum up the numbers in the middle, and then if I have a word in between, like here I have the word massa in between, I just add 1, so I get 89 instead of 88, and then I keep track of the words on the end. And then at the end, I find out that I have 197 words in my file. So cool. So this is an example of compositional reasoning. That is, the append of the word count should be the word count of the appended strings. And we'll also want the property that appending the word count of the empty string to any word count should be the same as the word count of that string, right? So we want to preserve both the sort of concatenation property and also the identity property. So when we say compositional reasoning, we usually actually mean homomorphism, which is the category theory term for this kind of property. So this is an example of a monoid homomorphism. Homo means same, and morpha means form. So it sort of preserves the form of the monoid. So we're in the string monoid, and we're going to the word count monoid, and we want to preserve this structure. And there are lots of other monoid homomorphisms like this. Here's an example of one, where if you take the length of two strings and add them together, that should be the same as the length of the concatenated string. Right, so it has the same structure on both sides, and then the length of the empty string should be 0, which 0 happens to be the identity for addition. Right? And this is the real plot of category theory. Category theory is really about studying homomorphisms. It's really about comparing structures, comparing categories using homomorphisms. Okay, so not only is every monoid a category with one object, but you also have a category of monoids, where the objects are monoids, the arrows are these monoid homomorphisms, and the composition is just function composition. And the composition is going to have the property that a composed, two monoid homomorphisms composed are also going to be a homomorphism. So we're going to preserve this monoid structure. But since monoids are categories, the category of monoids is a category of categories. But we can generalize that and release that the restriction that we're in just monoids, and to say that we want the category of categories in general, where the objects are categories, and now we want categories to be arrows to be category homomorphisms. And those end up being the functors. So another way of saying category homomorphism is functor. And then the composition is going to be functor composition. Cool? So a functor from the category C to the category D will just take every object in C to an object in D. It'll take every arrow in C to an arrow in D. And composition and identity will be preserved in the same way that composition and identity were preserved in the monoids with homomorphisms. Okay, so a functor from a category to itself is sometimes called an endofunctor. And particularly, we're interested in endofunctors in the category of Scala types and functions when we're working in Scala. And so such a functor takes a type T and turns it into a type f of T. And then on arrows, on functions, it will take a function from A to B and turn it into a function from f of A to f of B. Okay? And it will preserve the composition, so that you notice that this is sort of a homomorphism property. So map f compose G should be map f compose map G. So if we have a list, we map f over it, and then we map G over it. No, sorry, other way around. Map G over it and then map f over it. That should be the same as mapping the composite function f compose G over that list. And mapping the identity should do nothing. Cool. So this is another example of a homomorphism law, or compositional reasoning. Option is an example of such a functor. And sometimes in Scala, we're going to be working with functors to model effects. And here the effect of the function f is that f might not return a b at all. So it's takes an A and it doesn't return a B, it returns an option B, which might be none. So this might be a problem for composition because if we have F and G like this that both return options, we can't say F and then G. We can't compose them in the ordinary way, right? Because the option B is not compatible with B. However, we can say F and then flat map G. That is, we can simply flat map G over the result of F. Right, so we have this sort of notion of composition. It's just a little more complicated. So we can actually write that as a function that does this composition for us. And I'm going to write that using this sort of fish operator. I think it's how it's done in Scala Z and probably cats as well. So f fish G, we'll take F and G and go from A to option C, doing both F and G, and uses flat map for the composition. So these kinds of arrows from A to option B, or something to option something else, those arrows actually form a category. And those are called Kleisli categories. So then the objects in a Kleisli category are going to be the Scala types. It's going to be the same as the regular Scala category. But now an arrow from A to B is not going to be a function from A to B. It's going to be a function from A to option B. But it's still an arrow from A to B in this category. And then composition is going to be not regular function composition, but Kleisli composition, which is what we just saw. So the composition is not, F compose G compose H. It's, lambda of X, H of X, flat map G, flat map F, like this. And so it's associative, and it has an identity. And in the option case, the identity is sum. Yeah? Cool. And so whenever we have this kind of thing, we have a monad. Cool. So yeah, in general, in a Kleisli category, objects are types like this. And then an arrow from A to B is a function of type A to M of B for some functor M, which happens to be a monad because it has this property. And then Kleisli composition is the composition, which is flat map, and the identity is the unit for the monad. And we can write monad in Scala like this. So it just has a flat map and a unit like this. And you will notice that this has a homomorphism property, that flat map of F compose G, Kleisli composition, is flat map F compose regular function composition, flat map G. Right? So a monad is actually a functor or a homomorphism from the Kleisli category into the regular category. And I think that's kind of cool. And then flat map of the unit, which is the identity in the Kleisli category, becomes the identity in the regular category. So the structure of the category is preserved. And there are lots of these monads. For example, the list monad has the effect that F might return 0 or many B's. There is this sort of writer monad, which means that this F returns an extra C in addition to the B, which we might compose with other C's using a monoid. There's a reader monad, which allows us to have the effect of requesting an additional value of type R. And then there's a state monad, which will allow us to keep some state of type S, which might be used to construct RB. And then there's I/O, where the effect is that the function f might request some I/O effect in order to produce its B. So in general, a monad will describe some effect like this. And the upshot of this is that using monads, we recovered compositionality. So it's, we can have compositionality of effects using these Kleisli categories. Cool. So we had something that prevented composition and then resolved it. Okay. So in general, what kind of stuff prevents composition? And I want to say that there are a number of things, and sort of in general, they fall into a few categories. Punning on category here. Okay. So the first of these is whenever we have a connected sequence, we lose composition. Connected sequence is where the meaning of the whole program is not a composition of the meaning of the parts. So for example here, this is an assembly language program where I am moving the number 1 into the accumulation register, and then I'm calling the DOS interrupt. So this is a DOS program. And like, it's totally unclear what this does. Like, you have no idea, looking at the individual instructions, what they're going to do. The meaning of this whole program is actually that it reads from the keyboard and prints to the console, right? But there's no way that you can know that, even if you knew the individual meanings of the instructions. So the meaning of the whole actually depends on something external. And also, whenever we have a dependency, where the meaning of the parts depends on the meaning of some of all of the other parts, for example, in chess notation, whenever you see like n d5, you don't know which. So in chess, each player has 2 knights. So you don't know which player moved or which knight they moved. You just know that a knight was moved to d5, and you have no idea how that affected the game. And so the meaning of that move, actually, you need to know the whole history of the game in order to figure out what that means. And it's the same problem having dependencies in programs. Another problem that prevents composition is this thing I want to call leaky abstractions, where we're trying to force some structure into a space that's sort of too big or can represent too many things. For example, here I am forcing an SQL query, which is sort of a very constrained space, into a very unconstrained space, which is strings. So a string could be anything. And so now, let's say I wanted to modify this query by adding another select thing, and I want to add another condition to my where clause. It's not very easy to do using strings, because I don't know what the structure of that string is. So I would need to like parse it, and then do some kind of manipulation, or I could do some kind of horrible hack. All right, so we're working on a representation that is sort of too big and insufficiently precise and insufficiently abstract. Another thing that prevents composition is side effects. So here, for example, I have a cafe that has a single method, which is buy coffee. It takes your credit card, and it gives you a coffee, but in doing so, it charges your credit card. And so this is not very compositional, because if I wanted to say buy 2 cups of coffee, it would charge my credit card twice, which is probably not what I want. And so we can recover compositionality by using, for example, the writer monad, where I return a coffee and a charge, which I can then compose with other charges using a charge monoid, for example, at a later time, and then pass that to a payment system to be batched or something. Cool. And also, if we look at this sort of homomorphism property of map, so if we say map f compose g, and that should be the same as map f compose map g. So let's say that f and g print to the screen. Then this is not going to be true, because the thing printed on the left is going to be different from the thing printed on the right. Like let's say this mapping over a list. So if we say map f compose g, it's going to print stuff in the list once. And if we say map f compose map g, it's going to print stuff in the list twice. So having side effects is going to break this compositional reasoning. And the same with f of x plus f of y. Like if x is null, for instance, this is not going to be the same thing. Cool. So more than side effects and things like that, I want to say that the thing that really prevents composition is entropy and perplexity. So entropy is a measure of how many configurations a system can have. And so the more possible configurations a system can have, I want to say that the less possible composition is. And then perplexity is how difficult it is to predict which configuration a system is in. And both of these things are barriers to composition. So when we go from a low entropy, highly predictable structure to a high entropy, unpredictable structure, we lose information. So we're throwing something away, and we're losing precision, we're losing abstraction, and therefore we're losing composition. Okay, so here's your program. This is a block of TNT in Minecraft. And so this is a low entropy state, you know. And this is compositional. You can take two of these and put them together. But imagine that in Minecraft you could take, you know, composite blocks and build from those. Like, Minecraft is not as compositional as we might like. But, you know, we can build structures from this, right? So yeah, this is compositional. We can you know, build these beautiful towers of TNT, and we can sort of reason about how they fit together. That's pretty easy. But then when we go to a high entropy state, by actually detonating our TNT, we have no compositionality here whatsoever, right? So if this were our program, and we've sort of executed our side effects, we've lost the ability to extract the meaning and compose that meaning with the meanings of other programs. All right, so entropy, I want to say, is the opposite of meaning. I want to quote my good friend Ignacio Casas, who is a Scala aficionado. He's at Stanford University in linguistics. He says, without compositionality, language is literally meaningless. You know, he's talking about natural language here, but I want to say that this applies equally to programming languages. Now, if you imagine a natural language, a human language, having no composition at all, so the language would be essentially a collection of unrelated, totally non-uniform random strings, right? So there'd be no ambiguity, right? Because there's going to be no room for interpretation. Perplexity is going to be maximized. It's going to be impossible to predict the meaning of any string in this language. Like, it's going to have a different word for every moment in time that you observe a flickering flame. And like, for every object and every aspect of every object you've ever seen is going to have a different word. So such a language would be literally meaningless. But it's not all or nothing, right? So there are extents and degrees in life and in programming. So I want to say that language is meaningless and programming is meaningless to the extent that it lacks composition. So to the extent that we have connected sequences, interdependent clauses, interdependent modules and libraries, leaky abstractions and side effects, and entropy and perplexity, we are doing meaningless work. And I think that's a bad thing. So on the other hand, when we have compositionality, we gain lots of things. And one of those things is productivity. If we understand some components and we understand the rules of putting those components together, we can understand things that we've never seen before. Right? So completely novel constructs become understandable to us just by breaking it down. We break the problem into parts. We solve the parts with simple programs, with simple reasoning, and then we compose our solution from the smaller programs. Another benefit we gain is systematicity. So if we understand f of x and g of y, we also necessarily understand f of y and g of x. That is, if we can solve a problem with p, q, and r, let's say these are programs, p, q, and r, if we can solve problems with them individually, then we can also solve any problem whose solution is any combination of p, q, and r, as long as we understand the means of combination. And also, compositionality just works. If a system can be built at all, it can be built compositionally. And really, I want to say that compositionality is the only tool that we have in order to reason about large systems. Like, if you have a big system that has to do like shopping carts and warehouses and sending products to customers, you have no hope of reasoning about that system without being able to understand the parts and then assemble your understanding of the whole from your understanding of the parts. And the last benefit we get is aesthetics. That is, compositional software is just delightful to work with. It feels more clean, you know. To quote a friend of mine, you feel like a mathematician and an artist in a structurally sound, clean house. So yeah, part 2 of this book I wrote with my friend Paul is a tutorial on writing compositional libraries, and I invite you to check it out. So to learn how to write more compositional software. And so yeah, I want to invite you to write more compositional, meaningful code. Thank you.